Okay.
Okay,
Can you?
Yeah, Thangavelu, you can.
Oh, okay. Anyway, we can start. Welcome to the APRG seminar. And we are very happy to have Jotsaroop back in IISER, or at least giving a talk in IISER. And she will talk
Virtually.
about Hardy-Rellich and identities and inequalities for the Grushin operators. Yeah, you can start now.
Okay. Thank you for giving me an opportunity to talk here. The title of my talk is Hardy and Rellich Identities and Inequalities for Grushin Operators via Spherical Vector Fields and Bessel Pairs. And this is a joint work with Debdip Ganguly from IIT Delhi and Prasun Roychowdhury from NTU Taiwan. Well, there are more experts in the audience regarding this inequality, which I'm going to tell now. So one of the most important functional inequality in analysis is Hardy's inequality. It was proved by Hardy in 1920s, and it states the following: that if you have a compactly supported smooth function in Rn minus the origin, then F satisfies this inequality, and this inequality has many applications in PD, spectral theory of operators, and unique continuation, etc. And another related important inequality is Rellich inequality, with the higher order of the Laplacian. So it was proved by Rellich in 1956, and he proved the following inequality. So here the constants are different, of course, and you have, instead of the gradient, you have the Laplace operator, and here the weight is also different. Right? Here you have mod x squared, and here you have mod x power 4, and for n not equal to 2. So this inequality is in all dimensions other than n equal to 2, and F is compactly supported smooth function. And so it is known that the constants appearing in the above inequalities are sharp. So these two constants.
Jyoti, this is just simple. This is mod of fx square or fx4? No? In the relic thing?
Yes, it is square.
Square root.
In general, it is the pth version is also available. Then there is a bound on P, like in Hardy's inequality, but we are dealing with only P equal to 2 case here.
Okay.
So because of this higher power of Laplacian, the weight changes basically. And it is also known that there are no non-trivial extremizers of the above inequalities. So it is natural to expect remainder terms. Okay? And so in 1998, Gusub and Moradefem, they introduced the notion of Bessel pairs unifying Hardy-Rellich and Rellich inequality. So it's kind of characterizing the radial weights for which these kind of inequalities holds with better remainder terms. So before I state their result, let me introduce certain notions. So first definition is Bessel pair, and you'll see why this term is also coming actually. We say that a pair V, W of C1 functions is a Bessel pair on 0, R for R between 0 and infinity. If V and W if there exists a positive solution, okay, call it F on the interval 0, R of this ODE, second order ODE, okay? And we say that VW pair of C1 functions is a Q-dimensional Bessel pair on 0, R. If this ordinary differential equation, here you have rho is the variable, Q minus 1, admits a positive solution on the interval 0, R. And you see that this actually is coming from the radial part of the Laplacian, the Laplace operator, in the Euclidean setting, of course. Okay. So now I can state this result by Gusub and Moradefem. So let n be bigger than or equal to 1, and R is strictly between.
Can I go back to the previous slide? Rho is the variable, right?
Yeah, rho is the variable.
Okay.
Yeah, so what was the theorem? That V and W be positive C1 functions such that V has some near zero, it has some kind of a growth and it is integrable also from 0 to R. And if VW is n-dimensional Bessel pair, so n-dimensional means that here you will have n, and n is the dimension, Rn basically. Maybe I should have mentioned that. Then for all compactly supported functions in the ball around 0 of radius r in Rn, so this result is in Rn, then this inequality holds. Suppose V and W are n-dimensional Bessel pair and V satisfies this integrability condition, then this inequality holds. And conversely, if this inequality holds, they always assume these two conditions on V, then VW is n-dimensional Bessel pair. So this is a really nice result here. And well, they also, okay, I will come to that later. So, and in addition, so in their main theorem, they have many equivalent conditions. So another thing is that if in addition, W and V satisfy this pointwise inequality, then so these two things, that is VW being Bessel pair and this inequality, VW being Bessel pair and this inequality, they are also equivalent to this another inequality, which is called Hardy-Rellich kind of inequality. Because here you have some bounds on the Laplace of U in terms of the gradient of U. Here. Okay, I think I made a mistake. I should have put a gradient here. I'm sorry, this is a typo. Yeah. Okay. So this kind of relates generalized Hardy inequalities and this Hardy-Rellich inequalities. Here is a gradient actually. Okay, and it also characterizes the pairs V and W with some integrability conditions on V under which these inequalities will hold. So as an application, you see, if you take V equal to mod x power minus alpha and W is this, they will form a Bessel pair and there will be a positive solution also. Okay, and so you will get, and the constants here will be sharp actually. So alpha equal to 0 is the classical Hardy's inequality. And then in this same paper, they also establish Hardy-Rellich with explicit remainder terms, Hardy-Rellich and Rellich inequalities. Okay. Then Flynn, Lamb, and Liu, they obtained sharp Hardy identities and inequalities on Carnot groups in 2021 as a generalization of the result of Gusub and Moradafim in the subelliptic setting. Okay. And our goal is to establish Hardy's and Rellich identities and inequalities for the group vector fields for Q-dimensional Bessel pairs using spherical harmonics on the Grushin space. Okay. And the other thing what we will do is to identify the radial derivative and spherical derivatives of the, well, I will define what is this Grushin operator and deducing a Rellich identity involving the L2 norm of the radial and the spherical contribution of the Grushin operator. Okay, now let me define what is Grushin operator. So, so Grushin operator is defined on Rn plus 1. Okay, so xi is just the normal partial derivative and in I ranging from 1 to n, and capital Y is mod x del by del t. T is the last variable, we call it. We denote it by t instead of xn plus 1. And mod x is the Euclidean norm, standard Euclidean norm in Rn. And the Grushin gradient we define as this. Okay, x1 to xn, the standard partial derivatives in the first n variable, and then in the last variable we have this extra factor of mod x. And Grushin operator is defined as this. So basically it is the divergence of the grad and which will turn out to be like this. Okay. You can directly see it from here. Okay, so this is the Grushin operator. And in fact, more generally, we can also define, which is known as Bondy-Grushin operator. Instead of mod x, you can put mod x power alpha for alpha positive. And then the corresponding operator, the second order operator will be this Laplacian in x plus mod x power 2 alpha. Okay, this is also a typo. I'm sorry, I should have put y here. So here you see x is ranging from 1 to n and y is ranging from 1 to m. And here the Laplace operator will be in Rm. Okay. And Lg alpha is a hypoelliptic operator, even though it only for alpha and even integer it will satisfy the square sum condition of the Hofmann, but still it is for other alpha also it is hypoelliptic operator, and we will only focus on alpha equal to 1 and m equal to 1, right? That is what but our analysis actually goes through for any alpha positive and m in n. Okay, so now I'll just fix Lg alpha equal to 1 and m equal to 1. And then I'll define certain preliminaries related to do analysis for the Grushin operator. So we define this non-homogeneous dilation delta lambda xt. Xt is a point in Rn plus 1 as lambda x. So lambda x is this usual dilation in Rn and lambda squared t. Then you can just check that if I take F composition delta lambda, apply the Grushin operator, you will get lambda square Grushin operator applied on M, then dilation. So under this dilation, it's homogeneous of degree 2. And another important thing is to define homogeneous, the corresponding homogeneous distance function from the origin, which is defined like this. So you see the difference from the usual Euclidean distance because of the difference in the structure of the Grushin operator. And from the definition, it is easy to check that if I apply the dilation, calculate the distance, then the factor of lambda will come out and then multiplied with the distance of xt from origin. And the corresponding homogeneous dimension is q. Q is equal to n plus 2 here because of this square in the last variable. Then we define the ball with respect to this distance function as BR0. O is this origin, which is 0 is a vector in Rn and Rn plus 1 basically. All the points xt such that rho xt is strictly less than r. So we will work with these kind of objects. So this is the first theorem. Let G be the Grushin space with dimension q. Q is bigger than or equal to 3, of course, right? Because q is n plus 2 and n is bigger than or equal to 1. And BR OB as defined above for r between 0 and infinity. And if VW is a q-dimensional Bessel pair, so here you see the q is coming here instead of n. The Euclidean dimension, you have the homogeneous dimension with positive solution f. Then for all CC infinity function, this holds. So you see here we have identity basically. So you remember the Hardy's inequality, you just have this weight function bigger than or equal to this. Here this exactly measures that what the difference is.
So what was rho here? Rho is the distance or rho is
I actually will define, you can write the measure in terms of like we do in the Euclidean case in terms of polar coordinates.
Or rho is the distance, the distance.
And rho actually, okay, we don't need to write here.
Can you go to back to previous slide little?
Yes, rho is the function of x and t, so you can.
That's homogeneous now.
Yeah.
Oh yeah.
It's a function.
Okay. Yeah. And rho is the norm.
Right?
Yeah.
Okay, so this is an identity, and this kind of nice identity you get thanks to spherical harmonics. That is the power of spherical harmonics here, and unfortunately we cannot do this on Heisenberg group. Okay, and the second identity is, well, I will define this. So it is just that instead of the whole gradient, if you take the radial part of the gradient, you have the corresponding identity again. This is useful for our purpose later on. All right, so now as an application, you see if V is 1, for V equal to 1 and W equal to this, they form a Q-dimensional Bessel pair with F rho as this. And you can immediately put these V and W there to get the classical Hardy's inequality. And actually, you can take R equal to infinity also in these situations. And then this implies Hardy's inequality for the gradient. And more generally, you can take rho power minus alpha. And then W will be this. It forms a Q-dimensional Bessel pair with F rho as this. Okay, I'm sorry. This is again a typo. I should have, because with alpha this also changes. It should be minus alpha inside the bracket. Okay, and if alpha is less than or equal to Q minus 2, then the above the equality. Actually, I should have said inequality can be, because here this. Let me go back here. So this is a positive term, and you will just get bigger than or equal to, and as soon as alpha is less than or equal to Q minus 2, it becomes locally integrable, and it can be extended to all CC infinity functions in Rn plus 1. Okay. And the proof actually is quite simple. It follows from spherical harmonics corresponding to the Grushin operator, developed by Garofalo and Shen in 94. Actually, they developed the notion of spherical harmonics on Grushin operator to prove unique continuation. Okay, so now I will define some spherical harmonics, but before that I need to define the polar coordinates with respect to this norm, the homogeneous norm for the Grushin operator. Okay, so actually we can write Rn plus 1. So here, because of the kind of inhomogeneity compared to the Euclidean thing, the powers are slightly different. So x1, so rho is that norm, right? Mod x power 4 plus 4t square, 1 by 4th root of that. Every point in Rn plus 1, except on a set of measure 0, can be, there is a diffeomorphism from Rn plus 1 to these coordinates. Okay. And R is mod x. And in terms of polar coordinates, this is just a function of, yeah, you can, well, this quantity is important for us because it comes in the Grushin operator. Well, maybe I'll come to that later. And so another thing which we need to also compute is the gradient of the rho mod square, which is just a function of which actually is equal to mod x square by rho square, which is this quantity.
Jyoti, can you go back to the previous slide?
Here?
Just hold it 1 second. Wait. Yes.
Is that okay?
Yeah.
And then, using this change of variables, you can write the integration, the usual Lebesgue integration on Rn plus 1 in terms of these polar coordinates like this. Okay. And here omega is the standard sphere in Rn. Okay. And because we are in Rn plus 1, so we have n spherical coordinates. And consider the rho sphere on the Grushin space as follows. So omega is this set, the sphere, a rho sphere, where this norm is equal to 1. Then change of variable arguments will give you this identity, which from here you can just plug in here, and if I define d omega, the measure on omega is this, then you will just get a factor of So this is actually, if you recall, this is nothing but mod of the gradient of rho. I mean the Grushin gradient of rho. So you will see that how these things appear in the Hardy's and Rellich inequalities. Okay. Now that we have defined the polar coordinates, just like in the Laplace operator, the standard Euclidean case, you can write Grushin operator in terms of polar coordinates in this way. So you see this, the grade mod of mod square of gradient of rho is coming here, psi, and then these are, so L sigma is a, you can say it is a Laplacian on Grushin rho square, which will only involve derivatives with respect to these angular variables, pi and omega. So this is the nice thing about Grushin operator, okay, that it separates the radial and this common factor outside, which is not a function of rho, but it is still outside. So we can deal with it by putting in the weight and this rho and the angular variables separately. So that makes the analysis very nice. And but those who know Heisenberg group, they know that there is an extra rotation operator which also comes here. So that is the biggest drawback of the sub-Laplacian on the Heisenberg group. To deal this, to use this technique in that. Okay. And the radial Grushin gradient and the radial Grushin operator are defined as follows. Okay. So you can see it from here. We are just taking the radial part. Then now I will come to spherical harmonics. And Garofalo and Shen, they proved the following, that we can write a function on Rn plus 1. First you use the polar coordinates in terms of spherical harmonics. Basically you fix rho and you have this phi k is an orthonormal system of spherical harmonics on L2 of omega. You remember we wrote the integration on Rn plus 1 like this. So what you do is you first, for a fixed rho, you do the orthonormal expansion on omega. And then those coefficients will of course depend on rho, right? Because this is the, so he explicitly calculated what are these pi k's. And then we also know that how this the Laplace on the Grushin sphere acts on phi k. Okay, so it is explicitly known, just like in the Euclidean case. So now what I will try to do is I'll try to give you a sketch of the proof of the theorem for the this theorem. Let me actually this theorem. Okay, so so it's actually very simple-minded proof. So what we do is you write U as a product of the positive F times V. Okay. You just multiply and divide by F, where F is the positive solution of for the Bessel pair V and W. Okay. And for V, you write the spherical harmonic decomposition because we want to measure the gradient of U, right? So we'll calculate both of these things. V gradient G U mod square and gradient V mod square. Okay. First you calculate this and using the ortho, you calculate it on the ball of radius R around 0. Using the polar coordinates and the measure in terms of these polar coordinates, we'll get this. And also the orthonormal properties of these phi k's. And then you just expand it. Okay, you expand the expression. Right. And then, of course, you will have to do integration by parts here. Because what do we want is, we want to get rid of the derivative on u, right? So we will try to do integration by parts cleverly to get this expression in terms of yeah. So this is a bit technical part, and similarly you do the same kind of decomposition for u, for gradient of u by f, and then you subtract them, and then you will see that whatever is left will be just these terms will get cancelled, and whatever is left will correspond to the ODE satisfied by V with a positive V and W, which has a with the F as the positive solution, and then we will be able to write in terms of W basically. The remainder here will be exactly integral W rho mod U square. Okay, that is the thing. Okay, yeah. So now I will state the Hardy-Rellich inequality here. So what it says is that, again, let V and W be Q-dimensional Bessel pair with positive solution F. Okay, so this is just for the radial functions U. Okay, so it says the following, that yeah, so when you take the higher order Laplacian and the Grushin Laplacian, you have to put some weight, okay, to use the. So yeah, this is natural, and this factor also comes in other kind of geometric objects where this is not constant. Like in the Euclidean case, this is 1, so it doesn't appear. Yeah, so you see the good thing here is that even the Hardy-Rellich is an identity here. Yeah, this may seem a bit technical, but the main, if you go back to the classical inequality, it just says that this is bigger than or equal to this quantity. And here it will give you that how much bigger it is in the exact estimates. Okay, and for V equal to 1 again and W equal to rho power minus 2, and the constant also will come. You can get much better inequality for the yeah, for this Hardy-Rellich. You will get much better remainder terms here, right, for the Hardy-Rellich inequality. Okay, right. I think I will not go into the proof. I had written something, but it may be a bit technical. So, and here also we will use the fact that V and W are Q-dimensional Bessel pair, and you use integration by properly. Okay, I think I will skip this because it's a bit.
I have a small question here.
Yeah.
The thing is, in the look at the statement little bit. See, the thing is, if you are taking this F is any positive solution, right? So, what happens if
Not
there
any
are two positives
of that equation? Yes.
with that B comma W be equivalent with positive solution? Means that solution will be unique or what?
No, it need not be.
But the thing is, suppose there is another solution G. Then this thing actually will be true for G also. That means this third quantity that completely depends upon F. So that is that third quantity is independent of F or G? No. Or
that depends on
this quantity, third quantity depends upon F, right? Is this theorem is independent of any positive solution?
Independent. No, so see, in the end,
are you getting my question?
Is an identity actually, and for radial functions. Yeah, this part will be constant, no, for other solutions also.
So.
Right?
It has to be, right?
Huh?
Yeah, it has to be, right?
Yes, because it's an identity.
Okay.
Yeah, I will skip the proof. So yeah, it is worth, so I'll elaborate on some remarks. It is worth noticing that the above theorem is an identity instead of inequality. And actually the identity also holds for general U. The only difference will be that you have to just replace the Grushin operator by the radial part of the Grushin operator and the gradient by the radial part of the gradient. Now we will state the Hardy-Rellich inequalities for functions, not necessarily radial. Yeah. So let again VW be and U be as in theorem 5. So here you see we have this inequality. Instead of the identity, you will get an inequality. And another condition on V is that in getting for this to hold is that V has to satisfy this inequality again. So V has to be well, I should have written twice differentiable for this to make sense. Maybe I did not specify that. Okay. So this kind of condition also comes in the Euclidean case on V, but that also involves W. Okay. But here this is independent of W, so that's a better situation in some sense. And again, you see, you put V as 1 and the corresponding W, you know what it is. And F also you can get. And so yeah, you will get this much better inequality with better remainder terms. And then this assumption, which I said, this assumption here on V is not too restrictive. In fact, in this work of Gusub and Moradafem, this assumption was introduced involving both V and W, and as I have already discussed, so this is less restrictive, and this provides a large class of Bessel pair for which this is satisfied. And but such an assumption, which only depends on V, was also first established by Berkio, Debdip, Ganguly, and Prasun, Roychowdhury in their work on hyperbolic spaces. So this is a different phenomenon other than the Euclidean, which is coming up here. And as an immediate consequence, we will see that the Hardy-Rellich inequalities with non-negative remainder terms, we obtain the following corollaries for q bigger than or equal to 5, because this comes because of the condition on v and its derivatives. So if you put v equal to 1 and the corresponding w is 1 by rho squared with this constant, yeah, so we are just not putting the term, yeah, this will be f here. Okay. So you can just put that v and w there in that theorem, and you'll get this inequality. And this is Hardy-Rellich. And then using the Hardy's inequality on this, you can get the Rellich inequality, which is again very sharp. Okay. Okay. Yeah. Fine. Now I will come back to like here. Let me see. So yeah, we are getting an inequality. Well, V and W are q-dimensional Bessel pair. Okay. So yeah, but we can do something for a particular V and W if we define what are spherical vector fields corresponding to the Grushin operator. So let me define that. So we define Lj as del by del xj minus del rho by del xj del by del rho. So it's like, yeah, separating out the rho part if you use the chain rule from the xj variable, and similarly in the t direction, ln plus 1. So j is from 1 to n, and you have an ln plus 1. Okay. And so So rho is very explicit, so we can actually compute what this quantity is here. And similarly, del rho by del t. And in the Euclidean setting, so these spherical operators, they were defined by Neil Bez, Ozawa, Machiara, and they were also discussed in Evans and Lewis' work earlier. So what is the advantage of introducing these spherical vector fields is the following, that yeah, you can prove that the Grushin operator is equal to, so you remember what L rho G is? It is the radial part of the Grushin operator plus this sum of squares of Lj square. Right. So this identity, so, we can prove using this explicit expression. Okay. And this is actually very useful now, because what happens is that I did not write it here, I think. Okay. So if I actually take the gradient of the Grushin operator of u mod square, you will see that it will be the sum of the squares of the radial part plus Lj u. Okay, maybe I should have written here. But anyway, I've written in the identity for the Grushin operator. Right. So once we have this, so yeah, we prove this identity using properties of these. So there are some more properties which these spherical vector fields satisfy. And so the above identity leads us to the following theorem, which compares the Grushin operator with its radial and spherical components. So this is the advantage of using this decomposition. And this holds for all u in CC infinity. So we have an identity for all compactly supported smooth functions away from 0 and q bigger than or equal to 4 as this. So you see, yeah, here, yeah, the earlier identities involved v of rho and w of rho, but here actually v is 1. Okay, and but yeah, here we are not talking about w. So we are not talking, I mean, in general, for general q-dimensional Bessel pair. So yeah, this is for a particular v and w, but still we have an identity, which is a very strong thing. And now you see, yeah, so every term is a positive term here. Okay. And if we go back to theorem, really have to go. Yeah, theorem 5, which is again an identity for radial functions, and as I've mentioned in the remarks, that we can also get this identity for general functions, just that we will have to replace the full Grushin operator by the radial part of the Grushin operator, and even the gradient also. Everywhere you just have to replace by the radial part of the corresponding operators, and we'll still have the identity. So then what we can do is use this identity for the radial part in this theorem here, and then you will still get an identity actually for right. So we'll get a Hardy-Rellich identity for general u radial. And actually, again, using the identity for the Hardy's thing, we will get the Rellich identity for general u, but not for general q-dimensional Bessel pair. For v equal to 1 and w equal to rho minus 2 times that constant, which is q into q minus 4, 16. So, and then here we have the exact positive Remainder terms. So that's the thing. That's the one of the sharp thing which we have. So yeah, as I mentioned, it provides classic Hardy-Rellich and Rellich identity for functions not necessarily radial, and utilizing theorem 5, we obtain the desired identities with sharp constant and exact remainder terms. Sorry. Okay, I think I still have some time, and I had skipped a proof of the theorem. Then maybe I can actually, I was just worried that I'll not be able to finish. So I may give a sketch of the proof of this theorem, which is actually quite simple-minded. Yeah, this Hardy-Rellich identity for radial functions. Okay. Right. So again, let's, yeah, this quantity, we assume it to be, this is a function of just an angular variable. We put it as psi. And then we observe that for radial functions, the gradient u mod square is actually this. Okay, because only the derivative with respect to rho survives. And then using polar coordinate decomposition. So yeah, we want to calculate this. I mean, this equal to W. I mean, we want to estimate this basically. So what we'll do is, right. So when U is radial, actually this is quite simple. So we know already what is the Laplace, the Grushin operator, right, in terms of radial and angular paths. And if U is radial, only the radial part will survive, right? And then what you can do is you have square and there are some weights. So you expand the square. Okay. And we want to estimate it in terms of lower order terms in U, right? In terms of the derivatives in U. So, so what we will do is once you expand it, and then we will deal with, we'll separate, everything is positive, and we are anyway assuming U is real valued here. So that is why I'm not putting the mod. Then we will deal with each of the terms and try to reduce the order of the terms because using integration by parts, obviously. Okay. So let us deal with the first term. It has the maximum, I mean, it's square of the second order. Okay. So, but what we can do is, it is del square by del rho squared. That can be written as the gradient of u rho, where u rho is the radial derivative of u. Right? And here we already, so this, we can use the Hardy's identity on for the Grushin gradient, and we'll get this identity again. Okay. And now that we have, so here we have been able to reduce the order now, right? From second order, we have come to the first order, which is good enough for Hardy-Rellich. And this is again a remainder kind of term, which depends on the positive solution, as Muna had already mentioned. Okay, so we cannot do anything more with this. And similarly, here is anyway lower order, right? It is gradient of u when u is radial square. And this one can be written as gradient of u square kind of thing, and then use integration by parts actually to get these kind of terms. And what we do is we then just write. So you have this I2 plus I3, well, I remove those parts. So we will get this I1, this equal to I1 plus I2 plus I3. So I1 is already this. And then when you combine all the terms, we will get the identity. So you see the radial part is, when we are dealing with only radial part of the operators, it is quite straightforward. But when we deal with the general Grushin operator, which is here, we cannot get an identity basically because yeah, so we have to deal with the spherical part, and you cannot get an identity using these methods. But well, I have not written the proof here. It involves the use of spherical harmonics and then clever integration by parts and separating the terms which are problematic, and then in the end it boils down to this kind of condition for this inequality to hold. So basically you take the difference, and then whenever this happens, this is bigger than or equal to that. Okay. So yeah, and well, I have not mentioned, so using these Hardy's inequalities and Hardy-Rellich inequalities, one can also prove uncertainty principles. And another worth mentioning thing here is that in the work of Grushin and Mohali, they always assume that V and W are positive C1 functions. But actually, when we use spherical harmonics, we don't need the condition on W to be positive. And here also there is no condition on W. So this, in some sense, this is more general. Because if W is negative, I mean, there is nothing to prove, but in general, W can be oscillating also. So, which also is so then you can use these kind of inequalities to prove hydrogen uncertainty principles and other more general things. Yeah. So I think I will stop here. So these are the references. This is the paper where they first unify all these Hardy-Rellich inequality, the weighted for the radial weights. And in this paper, they deal with these inequalities on the Carnot groups. And here they are not using, in this paper, they are not using spherical harmonics, and they use some identity because it is sum of squares of things. So they use certain identities. So in this paper, Garofalo and Shen, they developed the spherical harmonics for the Grushin operator, and then some more references. So I think yeah, I'll stop here. Thanks for your attention.
Thank you very much for a nice talk. I suppose there are some questions.
I can ask one or two questions. What is the condition? You have some condition on V. What is the integration of V here at to the power n minus 1?
No. So for one way, you don't need that condition. Okay. For if and only.
Can you show me that condition a little bit?
Yes. I think. Here. Yeah. So.
Yeah.
For one way, when VW is a Bessel pair and the inequality, you don't really need that condition. So going in the backward direction, you need this condition. So in the for the the hyperelliptic case, we will have Q minus 1 actually if we want to go in the backward direction. That okay?
You have mentioned that. Yeah. You have mentioned that somebody has done these results for hyperbolic spaces, right? These results are also.
Yes.
So I just wanted to see what is the condition on V they have to take.
V.
It is really R to the power n V. This condition 0 to.
As I said, one way implication will not involve any condition. So you see this the classical
no.
Is if and
No, what I am saying that for hyperbolic spaces. So is there any change in condition on this and in the backward direction? Or you don't know?
What condition?
The integration of from 0 to R to the power n minus 1, where dr is infinity and
No,
1
no.
by.
What I'm saying is that if V and W are Bessel pair, then this inequality holds will not require any integrability condition on V as such. Okay, for CC infinity functions away from 0 and n. Okay.
Hmm.
So yes, let me go to here for the. So the condition is same. If Debdip is here in the audience, he can tell better. Maybe I don't know if he's there. Let me. Sorry. Yeah. I just wanted to go to the inequality part actually. Yeah, this one. So if V and W are Bessel pair, Q-dimensional Bessel pair, there they have the Euclidean dimension, then this will hold, where Q is replaced with the Euclidean dimension. But if we want to prove the converse part, then we need to have more conditions on V. Is that clear?
Yeah, that is
Integrable.
clear. But yeah,
So this
but my
is also one way you can prove it directly.
directly, but
Because in the proof, I didn't know if I was very clear with the proof, but at least the simple parts will not, they are not using any, I mean, as soon as you have polar decomposition, spherical harmonics, you can do that. But yeah, yeah, these kind of conditions, they are different than the Euclidean condition.
I have to see at that. Okay, thanks. Okay,
Hmm?
I don't have any question. Yeah, I will see it probably.
Okay.
Jyoti, in the theorem 3,
Theorem 3. Okay. Yes.
Yes.
so here in the converse part that that if the above inequality holds, then BW is a dimensional n-dimensional Bessel square. So is like, could you briefly say how this inequality prove the converse part here, at least in the Euclidean case? Like, does it easily follow or?
No, it does not easily follow. So what they look at is some kind of a super solution of some elliptic PDE, and then yeah, then they try to construct a positive solution for that ODE from that.
Mm-hmm.
Is that okay? So because this can be written as, you know, yeah, they find the PD like divergence of V times grad of U
Mm-hmm.
minus W of U equal to 0. Okay. If they can, so with some boundary conditions, so if they find a positive solution of that PDE, then they try to construct the positive solution of that one-dimensional Bessel equation by integrating over the spherical coordinates.
Okay. So and so in the case of hyperbolic space, they all the same, at least the analog of this whole, like they also give this if and only if condition in the hyperbolic setting.
I have seen one way. I think the
Okay.
other way, same thing will work in other situations as long as you have some kind of Harnack inequality. So you have to prove the existence of the super solution, and that requires some kind of Harnack inequalities. If you have that, you can prove that in other settings also.
And while proving this sufficient condition that the inequality holds, this integration over 0 to r to the power n minus 1 vr dr less than infinity. So this is this saying that sort of b as a radial function b on rn, this b should be integrable, like this kind of condition is can
Local
be
integrability condition, yes.
yeah,
And this
but here can be r equal to infinity. That's why I'm curious. So that's
yeah,
why
so
okay.
yes, and this is like near 0, that it cannot grow too much, no, because it is yeah.
Okay.
It has to do with the local integral, because here you see we are not removing 0 also in this inequality. No? We are not looking at VR 0 minus 0, so minus the origin. So that is why here you need to have some kind of integrability conditions.
Okay. Thank you.
Yeah, stop sharing.
Are there? Yeah, maybe. Are there some more questions? Probably. Looks like there are no more questions. So, thank you once again.
No problem.
Yeah, you can stop sharing.